And so what we're getting is we're just getting a kind of a variety of methods for integrating things that before we couldn't integrate. So we know how to integrate products of functions that maybe, we couldn't integrate before. Sometimes we use integration by parts. These algebraic functions where we have quantities that involve something of an a squared plus u squared, a squared minus u squared, or u squared minus a squared. If we can't do those with basic techniques that we did before, maybe we can use trig substitution. Sometimes trig substitution is a painful process. What if, for example, I gave you this problem and I said, okay, do that with trig substitution. Well, okay, I guess I can. I mean, if I didn't tell you what to do for that problem, do you think you might try just breaking it apart first? I would. If we broke this apart, if you just gave me this problem, I'd say, okay, let's try breaking it apart. If we broke that apart the way it looks here, I would have 5x over x squared minus 1 dx. Great, I can integrate that part with just a plain old substitution, a generic one that we did back in section 5.5. And then I would have plus the integral of 1 over x squared minus 1 dx, which is not quite as pleasant. But let's do this easier part first. For this part, I would just let u equal x squared minus 1. And if u is equal to x squared minus 1, then du will be 2x dx. So I already have the x and I have the dx, so I'm going to multiply by 2 and reverse it with a 1/2. And then I'll just factor that 5 out front. So I will end up with 5/2 times the integral of du over u. So that part we've done before, yeah? So this would just be 5/2 the natural log of absolute u, or 5/2 the natural log of absolute x squared minus 1. But that's just from the first part of that fraction. I also have to integrate this one. Now, if I had an x up there, it would have been great because I would have just done that. But I don't. And so with what we know now, what I would have to do is a trig substitution. Since this is a u squared minus a squared, the substitution that I would make is x equals 1 secant theta. So I've already done the 5x over x squared minus 1. We've already integrated that just with a plain old substitution. And now we're going to integrate the remaining part of 1 over x squared minus 1 using a trig substitution. So there we would have dx is secant theta tangent theta d theta. And x squared minus 1 would be secant squared theta minus 1, which is tangent squared theta. So for this integral, we would get the integral of 1 over x squared minus 1 is tangent squared theta times dx is secant theta tangent theta d theta. So we could cancel this tangent with one of those, and we have the integral of secant theta over tangent theta d theta. And now what do I do? Well, for secants and tangents, what we typically do is we try to pull off either a secant tangent and rewrite everything else in terms of secants, or we pull off a tangent and write everything else in terms of, or pardon me, we pull off a secant squared and rewrite everything else in terms of tangent. I don't have that option here. So on this one, I'd probably try just going back to sines and cosines. This would be 1 over cosine theta over sine theta over cosine theta. Invert and multiply, those guys cancel. and we have the integral of 1 over sine theta, which is the integral of cosecant theta. Luckily, we know what the integral of cosecant theta is. Now this part is just coming along for the ride. This whole integral was done, and I'm going to take that answer and I'm going to add it to the answer that I get over here. What is the integral of cosecant theta? Well, it's negative the natural log of absolute cosecant theta plus cotangent theta. And then I still have to break that back in terms of my original variable. If this is theta, the substitution that I made was x equals 1 secant theta, so secant theta is x over 1, and secant is hypotenuse over adjacent. So this would be the square root of x squared minus 1. And we would get, from this integral, we would have 5 halves the natural log of absolute x squared minus 1, plus a negative, I'm just going to write it as minus the natural log of absolute cosecant theta is 1 over sine, so that's hypotenuse over opposite, plus cotangent theta is adjacent over opposite, and then plus c. And we're done other than simplification. Now notice this guy really could be simplified quite a bit. We could combine terms. That would be the natural log of absolute x squared minus 1 minus the natural log of absolute x plus 1 over x squared minus 1 to the 1/2 plus c. And we could go ahead, if you'll notice that this is factorable, we could actually combine terms there and rewrite that in a completely different way. Can we integrate it that way? Absolutely we can. Perfectly reasonable way to integrate that problem. But what if I told you that that integral, the fraction that's involved in that integral, could be rewritten as this. If I told you that the integral of 5x plus 1 over x squared minus 1 is the integral of 2 over x plus 1 plus 3 over x minus 1, which way would you rather integrate it? How hard is it to integrate this version? Not very, is it? Just basically du over u and a du over u. So we'd end up with 2 times the natural log of absolute x plus 1 plus 3 times the natural log of absolute x minus 1, and we're done. I'm going to take your stunned silence as just awe at how easily we got that integral done, yeah? I just told you that was the same. Now, do you believe me? If you add these two fractions together, remember we'd get a common denominator. And so to put this fraction over this denominator, I'd multiply by x minus 1. So I'd have 2x minus 2 plus this one I'd multiply by the x plus 1. So that'd be a 3x plus 3, or I get 5x plus 1. But your question is exactly what we're going to talk about today. How did I know that this was equal to this? That is what we call partial fraction decomposition, and that's what we're going to talk about in this next section. Okay, so is it wrong to integrate it the way we did the first time? No, with the methods that we know now, that's the way we would have to do it. But if we can decompose a rational function into smaller, more easily integrable fractions and integrate it with no more problem than that, then we may want to investigate this method as well. So that's where we're going, is how do we take an arbitrary rational function and decompose it into the sum or difference of smaller fractions. So what we're doing is we're simplifying our integrand so that when we integrate it, we don't have to bring in the big guns of trig substitution necessarily. All right. Any other questions before we go on and talk about the actual process behind partial fraction decomposition? Oh, I forgot half my absolute value, didn't I? Absolute x plus 1. You bet. Sorry, I just didn't write it down, did I? All right. So what we want to do is we want to be able to take a fraction and decompose it into smaller parts. And this is guaranteed that we can do this by the fundamental theorem of algebra. We're not going to really mess with the proofs of this. That would be more for an advanced algebra class. We're just going to use the results, which are fantastic. But what we know is that if you have a rational function, where, and I mean by polynomial over polynomial, the denominator can always be reduced to a product of linear and irreducible quadratic factors. So to find the partial fraction decomposition of a rational function now remember, rational means I've got a polynomial on the top and a polynomial on the bottom. First thing that we're going to do is if the degree of the numerator is bigger than or equal to the degree of the denominator, simplify using long division first. The denominator into a product of linear and or irreducible quadratic factors. Two x minus 3x. Those kinds of things are linear factors. Irreducible quadratic factors are quadratics that we can't factor further over the real numbers. So things like, say, x squared plus 4. Now, if it was x squared minus 4, we could make it into x plus 2 times minus 2. But this one, since it's a sum, remember you don't have a formula for the sum of two squares. Or if you had something like x squared plus x plus 1, that's also irreducible quadratic. And I just dropped my pen. Okay, there. So for our function that we just had, we had 5x plus 1 over x squared minus 1. So when we factor that denominator, we'll use the difference of two squares, and that would factor into x minus 1 times x plus 1. Okay. Once we have the denominator factored, what we're going to do next is we're going to set up what we call the decomposition equation. Okay, so we're going to form a decomposition equation. What we're really looking for is we're looking for two or more fractions that when I add them together or subtract them from each other, I get this fraction. Now there's lots of possibilities out there. The process that we're going to do is just going to find us one of them. Okay, so we're going to form a decomposition equation by setting the original fraction equal to a sum of fractions, each having a factor of the denominator as its denominator. And when I say that, I mean each having a factor of the original denominator as its factor. For every function, if the factors are linear, the numerators are going to be constant. If the factor of the denominator is an irreducible quadratic, the numerator will be linear. So for every fraction in the decomposition, if the, let's say with a linear denominator, the numerator will be a constant. For those fractions with irreducible quadratic denominators, the numerators will be linear. And so when I say that, when I say that numerator is a constant, I mean it's just like a number A or B or C or whatever. And if the numerators are going to be linear, those would be something like a bx plus c, for example. So for our particular fraction, we have 5x plus 1 over x minus 1 times x plus 1. Our decomposition equation is going to look like the following. I have two distinct linear factors here. Both are raised to the first power. So in my decomposition, I am going to need one fraction with an x minus 1 in the denominator and another fraction with an x plus 1 in the denominator. If these had been raised to powers higher than 1, I'd have to have extra fractions, but we'll look at one like that here in just a minute. Okay. This is a linear denominator, so my numerator will be constant. This is also linear, so my numerator will be constant. Now, once we have that set up, what we want to do is solve for the unknown constants. In the numerators. So for example, on this one, we want to solve for A and B. Okay, now I'm going to pause right here because I'm about to have to take this page down, so I want to make sure you've had a chance to get it written down before I do. Just let me know when you're kind of ready for me to move to the next page. Okay. Okay. All right. Everybody else good? All right, so my goal is to take this equation and solve for A and B. Now, one method that will always do that is what we call equating the coefficients. Okay? What we do to equate the coefficients is the following. We take the least common denominator, which will always be the denominator of the original function, and we multiply both sides of the equation by that least common denominator. So I'm going to multiply the left-hand side by that least common denominator, and I'm going to multiply the right-hand side by that least common denominator. Now, this is fairly typical in that when you're solving an equation that involves fractions with the x's in the bottom, one of the things that we learn to do in college algebra is clear the fractions by multiplying both sides by the least common denominator. So that's where we're going to start. When I multiply the left-hand side by that LCD, I get just the numerator of the original fraction. Except I lost my 5x plus 1 there. Does help when you write down the original problem. Okay. So we'll have a 5x plus 1 is equal to, when I multiply this fraction times this product, the x minus 1's cancel, and we would just have a times x plus 1. When I multiply this fraction times the x minus 1 times x plus 1, the x plus 1's cancel, and we have plus b times x minus 1. Now, I only have one equation at this point, but I need to solve for A and for B. So what we're going to do is we're going to regroup. We're going to regroup this where all the terms that are multiplied by x are together and all the terms that are constant are together. So I'm going to rewrite this as 5x plus 1 is equal to ax plus a plus bx minus b. So I'm going to group the x terms together and the non-x terms together. So I will have x times a plus b, just factored an x out of those two terms, and then I have plus a minus b that are not being multiplied by x. Okay, here's what we do for equating the coefficients. Once we get it to this point, we say, all right, I want this left-hand side to be equal to this right-hand side. And I want to find an A and a B that will make it happen. So one way to think about that is if you want this side to be equal to this side, then I would need the same number of x's on the left as I have on the right. Well, how many x's do I have on the left? I have 5 of them. How many x's do I have on the right? I have A plus B of them. So we're basically forcing a solution by saying, okay, I want this to be equal, so I'm going to make it where this A plus B, which is the coefficient of x on the right, is equal to 5, which is the coefficient of x on the left. I also want the constant parts to be the same. So I'm going to set the constant part on the left equal to the constant part on the right. And so we'll end up with a system of equations with 2 equations and 2 unknowns. And you can just solve it with substitution or elimination. For this one, I personally would probably just add those 2 equations together, because when I do that, the b's would add out and I would have 2a equals 6, or a is equal to 3. If I know a is equal to 3, to find b, I'm just going to plug it back into one of the 2 originals. And I would get b is equal to 2. So if I take this value for a and this value for b, I can rewrite my original fraction. It was a over x minus 1, which would be 3 over x minus 1, plus b, which is 2 over x plus 1. And so we still have a lot of work we have to do when we're doing the partial fraction decomposition, but if you can get it broken down, the integration process is much easier. And so once we get it to that point, we would just integrate as normal. Okay, the kind of new part in this section and in this process is actually finding that pair of numbers a and b that make these work. And remember, this particular method only works for rational functions. You have to have a polynomial on the top and a polynomial on the bottom. And we already integrated that, which is why I'm not doing it again. Questions? Who's still here? Yes, please. I'm hoping you're still here and just being, quiet instead of just going, no! Right. Excellent. Okay, that's just fine. Oh gosh, that sounds like me. All right. So the big process here, and I know this involves some algebra, but the big process that's new is actually finding the decomposition. Most of the actual in this section, once you get the decomposition done, the integration part is not usually, as long as what it has been in the first couple sections, like integration by parts and trig substitution. You'll still have to do one of those on one of these, but most of the time the integration will be pretty straightforward. Okay, so before we do some more examples where we actually want to show you some, let's just say we had a fraction where the denominator factored into x times x minus 2 times x plus 3 squared. Okay. This actually has, if we multiplied it out, we would have an x squared from here times an x times an x. The denominator here would actually be a power of 4. or the degree of the denominator would be a 4. When you do your decomposition like this, all of the denominators, notice, are linear, but one of them is raised to a power higher than 1. So when you're getting this decomposition, you have to take into consideration that you may have had a fraction with x plus 3 squared as the denominator. So when you have fractions where the denominator has powers, or I should say factors that are raised to a power higher than 1, you have to include a fraction for that factor all the way up to the highest power to which it's raised. So we would need one fraction with an x as the denominator, one fraction with an x minus 2 as the denominator, one with an x plus 3, and one with an x plus 3 squared. Because it's not, we're just looking for a fraction that makes it work, but it is possible that we had both an x plus 3 and an x plus 3 squared in there. So you have to take that in as a possibility. And in these, since these are all linear factors, your numerators would just be constants. So if we had a fraction where we had x squared times x minus 3 squared times x plus 1 cubed, can anyone tell me how many fractions they think will be in the decomposition? What's the overall degree of that denominator if you multiplied it out? Not quite. I think we would add the exponents, right? Yeah, but yeah, you're thinking along the right lines though. So it'd be a 7, right? So we would actually need 7 possible factors in the denominator. So we would have one fraction for an x, one with possibly an x squared, another one with an x minus 3, another one with an x minus 3 squared, and then for x plus 1, we're going to have an x plus 1 to the first, x plus 1 to the second, x plus 1 to the third. All of those could have been factors in the denominator to get a decomposition like this, or to get a combination like that. Now, I'm not saying that this is the only possible combination of denominators. We're just trying to find that one that works. One thing that people typically get confused about is factors that look like this, because you see an x squared, you think, quadratic. But no, this is not an irreducible quadratic factor. That is a linear factor raised to the second power. So these would all have numerators. May have gotten a little carried away there, where they are just constants. Okay. So what if our original had something like x plus 1 times x squared plus 4? Then our decomposition would only have 2 fractions. We would have one for the x plus 1, and we would have one for the x squared plus 4. Since this guy is linear, my numerator would be just a constant. This is an irreducible quadratic, and so the numerator would be, b x plus c, or we would have a linear numerator there. Any questions about that part of the process? If you have an irreducible quadratic factor, then the numerator is linear, yes. But not here. Like this was a linear factor raised to a power. If it's a linear factor raised to a power, you can still leave the numerator as just a constant. It's only for the irreducible quadratic factors that we need a linear numerator. Okay, so I want you guys to take this fraction and just write down what you think the decomposition looks like. And then we'll compare and see if we can figure out what it is. Okay, so the integral will be x squared plus 12x minus 4 over x cubed minus 4x dx. So the very first thing you're going to want to do is you're going to want to factor that denominator and then set up a decomposition equation. So that's as far as I want you to get, is I want you to factor the denominator and set up a decomposition equation, and then we'll compare. And I'm going to go ahead and let you take a break in between. So we'll pick up at, let's see, if I give you 3 minutes to do that part and then another 5 minutes for break, we'll pick up again at 1:12. Sorry, I didn't realize it was this late. I should have let you go to break a little bit earlier than this. I apologize. So work on that for the next 2 or 3 minutes, and then we'll pick up at 1:12. What are you doing? What are you doing? You're a silly puppy dog. Yes. You're a silly girl. All right, so are we back? Or am I going to have to check roll again? All right, this denominator factors into x times x squared minus 4, which is x times x plus 2 times x minus 2. And so how many factors and fractions am I? Hello? Oh, okay. I was like, okay, can y'all hear me? It's three. It's three. Because we have three distinct. So I'm going to need a factor with an x in the denominator. I'm going to need a fraction with the x plus 2 in the denominator. And I'm going to need an x minus 2 in the denominator. Since these are all three linear factors, I just have constants in their numerator. Okay. So when we multiply both sides by the least common denominator, which is x times x plus 2 times x minus 2. So I'm going to multiply both sides by that quantity. The left-hand side, I'll just get x squared plus 12x minus 4. And on the right-hand side, I will have a times x plus 2 times x minus 2 plus b times x minus 2 plus c times x plus 2. Because remember, when you multiply this fraction times that product, the x's cancel, and you're left with just a times x plus 2, 1, and so forth. Okay? So if we're going to equate the coefficients, we will first have to multiply out the right-hand side and regroup it according to. This would be x squared minus 4 times a will be ax squared minus 4a. And then we have plus bx squared minus 2bx plus cx squared plus 2cx. So all I'm doing is I'm regrouping the terms on the right. So now I have x squared terms. I have an x squared times a plus b plus c. I have an x times, it looks like, negative 2b plus 2c. And I have a constant of negative 4a, because it's the only one over there that's not attached to an x with multiplication. And that's equal to x squared plus minus 4. So I'm just trying to find an a, b, and a c that make this equation true. If I had the same number of x squareds on the left that I do on the right, that would be one step in the right direction. I have one x squared on the left, and I have a plus b plus c times x squared on the right. I have 12 times x on the left, and I want that to equal how many x's I have on the right, and I have negative 2b plus 2c. My constant on the left is negative 4, and my constant on the right is negative 4a. So I also want those to be equal. And so notice now we have three equations unknowns, the more fractions you have, or if you have nonlinear irreducible quadratic denominators, you get more and more unknowns, and so you get more equations in your system. For us, we can still use a substitution and elimination process. If we look at this third equation, that guarantees that A is equal to 1. Plug that back into the first equation. And that will be that C is equal to 0, which would mean that B is equal to negative C. The only equation that I haven't dealt with is the middle one, so now I'm going to replace B with a negative C in the middle equation. And we will get 12 is equal to negative 2. B is negative C plus 2C. So that is equal to 4C, or C is equal to 3. And so we now know that A is equal to 1. We know that C is equal to negative C. That would give us that B is equal to negative 3. And hang on just for a little while too. I'll show you a different way that we could get that same result for a system of this sort. Alright, so my integral will be the integral of, where did I stop? Okay, so yeah, I'm still hoping for better internet someday. So we're going to have an A over X would be 1 over X plus B over X minus 2. B over X plus 2 is negative 3 over X plus 2, plus C over X minus 2 will be plus 3 over X minus 2. Integrate that term by term. Notice each one of these is just going to be a natural log. Natural log of absolute X. And then plus C. For me personally, I don't mind if you stop there. Sometimes now if you're looking at these in the book or maybe in my math lab, they may combine these using the laws of logarithms. You could write that as the natural log of absolute X minus natural log of absolute 2 cubed. Okay. And then combine using sums and products, or sums and quotients. So that could be written as the natural log of absolute X times X plus, or X minus 2 cubed over X plus 2 cubed, and then plus C. But that's just using the laws of logarithms and the product and quotient rule for logarithms to rewrite that. I'm perfectly happy if you just leave it right here. And I don't think they'll count it wrong in my math lab if you leave it there, but if they just write out an answer, they probably will combine those. Any questions? All right, well, you'll notice, guys, that the first, or the most kind of tedious part is A, B, and C. And so we do kind of have a shortcut method for those decompositions where you have non-repeated linear factors, we kind of can take a little shortcut here to finding A, B, and C. And we're just looking for an A, a B, and a C that work. So what we're going to do is we're going to pick some, quote, smart choices for X that make some of the terms disappear. For example, if I chose X to be 0, then this would be C times 0 times 2, which is 0. This would be B times 0 times negative 2, which is also 0. So the only one of A, B, and C that would be still in my equation would be A. So I'm going to solve this for A using X equals 0. So I would have 0 squared plus 12 times 0 minus 4 is equal to A times 0 plus 2 times 0 minus 2, and then that would be B times 0, C times 0. So those are gone. And I have negative 4A equals negative 4. So A is 1. Anybody have an idea about what another, quote, smart choice for X would be on this? 2. If we let X equal 2, the left-hand side would be 2 squared plus 12 times 2 minus 4 is equal to A times 0 plus B times 0 plus C times 2 plus 2. All the terms with an minus 2 in them become 0, and we would have 24 plus 4 is 28 minus 4 is 24 is equal to 8C, or C is equal to 3. And the last smartest choice for X would be negative 2, because it makes the other factor go to 0. We plug in X equals negative 2, we would have negative 2 squared plus 12 times negative 2 minus 4 is equal to A plus B times negative 2 times negative 4 plus C times 0. Or we would have 4 is equal to 8. Is that right? Let's see. I plugged in negative 2, right? Oh, yeah, okay. Right? And so what do we get there? We just get B is negative 3. Okay? And so we could find A, B, and C. I know it was still a little bit of work, but it was, I think, a lot less work than when we equated the coefficients. The problem is, equating the coefficients always works. This method only works this nicely when you have non-repeated linear factors. If you have repeated factors, or if you have irreducible quadratics, you won't be able to find all of them as easily because you won't be able to get all your terms going to 0. Now you could still do some combination of this and equating the coefficients, or plugging in other values and finding it that way as well. For those non-needed denominators. Any questions? X squared or an x minus 2 cubed, that's a repeated factor. If you have a factor that's raised to a power higher than 1, that's repeated. Okay, so First question, could I do trig substitution on this one? Yeah, I mean, I've got a nice, you know, u squared plus a squared there, but it's going to take me a while because I'm going to have to plug in for all these other terms and all that good stuff. But it would be doable. Whereas on this, the way it's written right there, since I don't have an a squared minus u squared, I'd have to do some factoring before I could even contemplate doing a trig substitution. So, okay. But for rational functions, when I can factor that denominator, I'm probably going to do it and do partial fraction decomposition. In this case, my denominator is already factored, so I am going to factor the 8 out front and not include that in my decomposition, just to make my numbers slightly smaller. It's perfectly fine if you leave it in as well. Your numbers would just look a little different because you would have had the 8 distributed through. So I'm going to decompose this fraction. So I have x squared plus 4 over x times x squared plus 8. How many fractions do you think I'll need in my decomposition? I have a linear factor of x, and I have an irreducible quadratic of x squared plus 8. And those are the only factors that I have in that denominator. The numerator of my linear fraction will be an a, and the numerator of my irreducible quadratic denominator will have a bx plus c. Now, it's possible when we work through this that either b or c ends up being 0, but we have to take into consideration the possibility that it's not. Multiply both sides by the least common denominator, and we'll get x squared plus 4 is equal to a times x squared plus 8 plus bx plus c times x. And so we will have ax squared plus 8a plus bx squared plus cx is equal to x squared plus 4. So that will be an a plus b times x squared plus cx plus 8a is equal to x squared plus 4. If we equate our coefficients, I have 1x squared on the left, and I have a plus b x squareds on the right. I don't have any x's on the left here, so that would be 0 x's on the left, and I have c x's on the right, so immediately I know that c is 0. And the constant on the left is 4, and the constant on the right is 8a. So we know c is 0. This would indicate that a is 1/2. And if I plug that back into the top equation, I get 1 is equal to 1/2 plus b, so b is also 1/2. And I end up with 8 times the integral of x squared plus 4 over x times x squared plus 8 dx would equal 8 times the integral of a over x will be 1/2 over x plus bx plus c will be 1/2 x plus 0 over x squared plus 8. So that's going to be 8 times 1/2 ln absolute x plus 1/2 times, if you let u equal x squared plus 8 there, then du would be a 2x, so I'm going to have another 1/2 times the natural log of absolute x squared plus 8. And then plus c. If you multiply through, we'll end up with 4 ln absolute x plus 2 ln of x squared plus 8 plus c. Now notice in this part I didn't need to leave the absolute values around the x squared plus 8 because x squared plus 8 is always non-negative for real values of x. Questions? Okay, we give you a couple minutes to write all that down. Let me know when you're done, and so we can look at one where we have a repeated factor. It's 1/4. You bet. Okay. Excuse me. Okay. I'm getting suspicious, so if you're still here, let me know. Okay, who is that? Oh, okay, sorry. I couldn't tell by your voice this time. So Zach's still here. So yeah, just a few people ditched us. Okay. So, you know, every time I check, it counts. So let's see. We have Miguel. We have Zach. Glenn, Eric, Annabeth, Brian. All right. Don't worry if I didn't say your name. I'm still looking. Yeah, don't worry. I'm still looking. So okay. So right. Got it. Okay. Pardon me? I did. I may not have said it though. Okay. Awesome. Now, let's look at, I'm going to have to stop doing that though, because then it begins to be a bonus, not a, we want it to be a good thing. All right, so we've got the integral of dx over x cubed minus 2x squared minus 4x plus 8. So what in the world are we going to do? The very first thing we need to do is factor that denominator. And one of the reasons I wanted to look at this one is it's one of those where if they don't have it factored for you and you haven't factored in a while, you might be a little bit hesitant about what to do. So oftentimes when we have 4 terms, what we do is we just factor using grouping. So I'm going to take these first 2 together and I'm going to factor out an x squared. So I have x squared times x minus 2 from the first 2 terms. And from the minus 4x plus 8, I'm going to factor out a minus 4. And I'll have a minus 4 times x minus 2 as well. So that would be x minus 2 times x squared minus 4, which is x minus 2 times x minus 2 times x plus 2. Or this fraction could be rewritten as dx over x minus 2 squared times x plus 2. So I'm going to decompose, I should say, 1 over x minus 2 squared times x plus 2. Because remember, that dx in the numerator is just like having a 1 in the numerator and multiplied by dx over here. So I will need 3 fractions in my decomposition. I'm going to need one for x minus 2, one for x minus 2 squared, and one for x plus 2. Since all of these are linear factors, even though this one is raised to a higher power, we would just have constant numerators. So when I multiply both sides by the least common denominator of x minus 2 squared times x plus 2, I get 1 is equal to a times x minus 2 times x plus 2 plus b times x plus 2 plus c times x minus 2 squared. Now, as I mentioned, it gets a little bit more of a challenge to do the quick trick when you have repeated factors or nonlinear. So I'm kind of going to do a combination here. I'm going to go ahead and set up for equating the coefficients. So that would be ax squared minus 4a plus bx plus 2b plus cx squared minus 4cx plus 4c. That's if I multiplied all that out. And so we would have 1 is equal to a plus c times x squared. So I've got that one and that one taken care of. And then for my x's, I have b minus 4c times x. That one and that one taken care of. And then for my constant, I have negative 4a plus 2b plus 4c. So if I was going to do this with just equating the coefficients, I have 0 x squareds on the left, so I would have 0 is equal to a plus c. I have 0 x's on the left, so I would have 0 is equal to b minus 4c. And my constant on the left is 1, so I have 1 is negative 4a plus 2b plus 4c. And I could just go ahead and do a substitution and elimination on this one to find a, b, and c, but I can probably save myself a little work by going back up and saying, okay, if I let x equals 2, then this equation would become 1 is equal to a times 0 plus b times 4 plus c times 0. Or that would be 4b equals 1, so b is 1/4. If I let x equal negative 2, this equation would become 1 is equal to a times 0 plus b times 0 plus c times negative 4 squared. Because if x is negative 2, this becomes a negative 4 and square it. So that would give me c is 1/16. And the only term that I don't know is a. But I know that a plus c equals 0, so if c is 1/16, then a would be negative 1/16. So it's still quicker than just solving this by brute force probably, but it's kind of a combination of using the equating the coefficients equations and the quote smart choices of x. So our integral would become it will be the integral of a over x minus 2 plus b over x minus 2 squared plus c over x plus 2 dx. And at this point, you've got to be getting to a point where you can integrate those really quickly. This would be negative 1/16, the natural log of absolute x minus 2, plus 1/4 times negative 1 x minus 2 to the negative 1, plus 1/16 the natural log of absolute x plus 2. Now remember, this one, we don't have a natural log involved because that's raised to the negative 2 power, not the negative 1 power. And there we have it.